brown dwarf. Brown dwarfs are the failed stars of the universe. They formed the same way a real star does, collapsing out of a cloud of gas and dust. But they never gathered enough mass to switch on hydrogen fusion in their cores. That makes them stuck in a weird middle zone, too heavy to be called a planet, but too light to be called a true star. Most brown dwarfs sit between 13 and 80 times the mass of Jupiter. They can fuse deuterium and sometimes lithium for a short while, but once that runs out, they just slowly cool and dim for the rest of time. Surface temperatures range from around 4,000 degrees Fahrenheit on the hot end all the way down to room temperature on the cool end. Matter of fact, some brown dwarfs are colder than a cup of coffee. They are extremely difficult to detect because they emit so little light, and astronomers think they might be nearly as common as ordinary stars. There could be billions of them, drifting through our galaxy, completely invisible to the naked eye. If you flew up to one in a spaceship, you would not see a glowing ball in the distance. You would see a dark, featureless sphere, only barely revealed by the faint infrared heat leaking off its surface. It would look less like a sun and more like a planet that forgot to find a star. Red dwarf. Red dwarfs are the most common type of star in the universe, making up roughly 75% of every star that exists. They are small, cool, and dim, with surface temperatures between 4,000 and 6,000 degrees Fahrenheit. Most of them are between 8% and 50% the mass of our Sun. The interesting thing about red dwarfs is how slowly they burn through their fuel. They are so efficient that their lifespans can stretch past 1 trillion years. For comparison, the universe itself is only about 13.8 billion years old, which means no red dwarf that has ever formed has had enough time to die yet. Every single one ever born is still out there burning. However, life around a red dwarf would be brutal. These stars are infamous for their violent flares, sudden bursts of radiation that can strip the atmosphere off a nearby planet in a single event. If you were standing on a planet orbiting one, the sun in your sky would look small, dim, and angry red, and every few weeks the entire surface of your world could be bathed in a wave of deadly X-rays. Despite this, red dwarfs are still considered places worth searching for life, simply because they are so common and they live for so long. They give the cosmos more time to experiment than any other type of star. Orange dwarf. Orange dwarfs sit in the sweet spot between red dwarfs and stars like our Sun. They are K-type main sequence stars with surface temperatures between roughly 6,000 and 8,500 degrees Fahrenheit, and they weigh in at about 60% to 80% the mass of the Sun. What makes orange dwarfs interesting is how stable they are. They produce far fewer dangerous flares than red dwarfs, and they live for 15 to 30 billion years, which is 2 to 3 times longer than our Sun will. That extra time matters because life on Earth took roughly 4 billion years to develop from microbes to anything you could have a conversation with. An orange dwarf would give a planet far more runway to do the same. If you were standing on a world orbiting one, the sky would look gentler than what we have. The sun would appear slightly smaller and would cast a warm amber light across the surface, almost like a permanent late afternoon. Many astronomers now believe orange dwarfs may be the single best type of star to look for habitable planets around. They are calm, patient, and they last long enough for biology to actually get going. Yellow dwarf. Yellow dwarfs are G-type main sequence stars, and our Sun is one of them. They have surface temperatures between roughly 8,500 and 11,000 degrees Fahrenheit, and live for about 10 billion years on average. Despite the name, yellow dwarfs are not actually yellow. From space, they appear pure white. The yellow tint we see from Earth is caused by our atmosphere scattering shorter blue wavelengths, leaving the longer, warmer wavelengths to reach our eyes. If you floated outside the atmosphere and looked at the Sun, it would look like a bright white headlight in the dark. Our Sun is currently about 4.6 billion years old, placing it roughly at the halfway point of its life. In another 5 billion years, it will start running out of hydrogen in its core and begin a slow, violent transformation. It will swell up into a red giant, expanding far enough to swallow Mercury and Venus, and possibly reach out and engulf the Earth itself. After that, it will shed its outer layers in a glowing shell of gas, and what remains of the core will collapse down into a white dwarf, ending its life as a slowly cooling ember, white dwarf. White dwarfs are not actually living stars. They are the leftover cores of stars that have used up all their fuel and shed their outer layers. A white dwarf is roughly the size of Earth, but it contains a mass comparable to our Sun. That makes it extraordinarily dense. A teaspoon of white dwarf material would weigh approximately 5.5 tons. If you could somehow scoop some of it onto your kitchen table, the floor, and probably the foundation of your house would collapse instantly. White dwarfs produce no new energy through fusion. They simply radiate the heat left over from their former lives, slowly cooling over billions of years. Eventually, in the very distant future, a white dwarf will cool down completely and become what is called a black dwarf, a cold, dark sphere drifting through space. However, the universe is not yet old enough for any black dwarf to exist. The cooling process takes longer than the entire current age of the cosmos, which means every white dwarf ever formed is still glowing. Even the oldest ones, from the very first generations of stars. Blue dwarf. Blue dwarfs are a theoretical type of star that does not yet exist anywhere in the universe. They are predicted to form when a red dwarf finally begins running out of hydrogen fuel. Instead of expanding into a red giant like more massive stars do, a red dwarf would slowly increase in temperature and brightness, shifting from red to orange to white, and eventually to blue over a span of trillions of years. The reason no blue dwarf exists today is simple. Red dwarfs live so long that none of them have ever reached this stage. The universe has not been around long enough for even the oldest red dwarf to start dying. Blue dwarfs are essentially a future event the cosmos is still waiting on. If you could somehow fast forward 1 trillion years and look up at the night sky, you would see something nobody alive today will ever witness. Dim red points of light slowly turning blue, one by one, as the smallest stars in the universe finally start to fade. Subdwarf. Subdwarfs are stars that look like regular main sequence stars at first glance, but burn less brightly than they should. They appear dimmer and bluer than expected because they contain very few heavy elements. In astronomy, anything heavier than helium is called a metal, and subdwarfs are extremely metal poor. That tells us something fascinating about their age. Subdwarfs are old, often among the oldest stars in our galaxy, and they tend to live in the halo, the spherical cloud of ancient stars surrounding the Milky Way. They formed in the early universe, back when the only ingredients available were the lightweight elements left over from the Big Bang. Heavier elements like carbon, oxygen, and iron only came later, after generations of stars had lived, died, and seeded the galaxy with their remains. So, when astronomers find a subdwarf, they are looking at a survivor from a much younger universe. It is essentially a cosmic fossil, still quietly burning billions of years after everything around it was born. Blue giant. Blue giants are massive, hot, and brilliantly luminous stars. Surface temperatures exceed 18,000 degrees Fahrenheit, and they can shine tens of thousands of times brighter than the sun. The term blue giant is a little loose. It covers a range of evolutionary stages, from massive stars just leaving the main sequence, to evolved stars in later phases of their lives. What they all have in common is a brutal trade-off. Because they are so massive, they burn through their hydrogen fuel at a terrifying rate. A blue giant might live for only a few million years. For comparison, our sun will last around 10 billion years. So if a blue giant and a yellow dwarf were born at the same moment, the blue giant would have lived, died, and faded into nothing before the yellow dwarf had even finished its childhood. If you were on a planet orbiting one, the entire sky would be flooded with harsh, blue-white light and intense ultraviolet radiation. Without serious protection, your skin would burn in seconds. These stars do not coexist with life easily. They are too bright, too violent, and they die too quickly for biology to keep up. Red giant. Red giants are stars that have exhausted the hydrogen fuel in their cores and have started fusing hydrogen in a shell around the core instead. This new burning layer pushes the outer parts of the star outward dramatically. A red giant can swell to tens or even hundreds of times its original radius. Despite their enormous size, their surfaces are actually cooler than a normal star, around 6,000 to 8,500 degrees Fahrenheit, which is why they glow with that deep red-orange color. Our own sun will become a red giant in roughly 5 billion years. When it does, it will expand far enough to swallow the orbits of Mercury and Venus, and it may reach out and engulf the Earth itself. Even if the Earth survives physically, the planet will be a glowing, molten ruin long before the sun ever gets close. Standing on the surface of a planet orbiting a nearby red giant would be unforgettable. The sun would no longer be a small disk in the sky. It would be a massive, dim red wall, taking up a huge chunk of your visual field, looking less like a star and more like a slow burning ceiling. Blue supergiant. Blue supergiants are among the hottest and most luminous stars in the known universe. They reach surface temperatures of 18,000 to 90,000 degrees Fahrenheit and shine hundreds of thousands of times brighter than the sun. They typically weigh between 10 and 100 solar masses, and they burn through their fuel at an extraordinary rate. Most blue supergiants live for only a few million years before destroying themselves. The difference between a blue giant and a blue supergiant matters. A blue giant is still burning hydrogen in its core. A blue supergiant has already passed that stage. It is what happens when the most massive blue giants run out of core hydrogen and start expanding and evolving. Most blue supergiants will end their lives in violent supernova explosions, briefly outshining entire galaxies. If you watched one of these explosions from a safe distance, you would see a single point of light suddenly become brighter than 100 billion suns combined, all in the span of a few weeks. Red supergiant. Red supergiants are the largest stars by volume in the known universe. They form when a massive star runs out of hydrogen in its core and expands outward into a colossal puffy sphere. Some red supergiants have radii exceeding 1,000 times that of the Sun. Betelgeuse, one of the most famous red supergiants and one of the brightest stars in our night sky, is so large that if you placed it at the center of our solar system, its outer surface would extend past the orbit of Mars and possibly reach Jupiter. Earth would not just be inside the star, it would be deep inside it. Red supergiants have surface temperatures around 5,000 to 7,000 degrees Fahrenheit, which is cool by stellar standards, but their sheer size makes them extraordinarily bright. They are also unstable and approaching the end of their lives. Most red supergiants will eventually collapse and explode as supernovae, leaving behind either a neutron star or a black hole. Betelgeuse itself is expected to go supernova at some point in the next 100,000 years, which is essentially tomorrow on a cosmic scale. Hypergiant. Hypergiants are the most massive and most luminous stars known to exist. They can emit millions of times more light than the Sun and contain masses exceeding 100 solar masses. They are also extraordinarily rare. There may only be a handful of true hypergiants in our entire galaxy. Hypergiants are deeply unstable. They lose mass at insane rates through powerful stellar winds, shedding the equivalent of entire planets worth of material every single year. They come in several flavors, including blue, yellow, and red hypergiants. One of the largest known stars, UY Scuti, is a red hypergiant with a radius approximately 1,700 times that of the Sun. If you replace the Sun with UY Scuti, the entire inner solar system would be vaporized instantly, and the star's outer edge would reach well past the orbit of Jupiter. Hypergiants live for only a few million years, and almost all of them are expected to end their lives in catastrophic supernova explosions, or, in the case of the largest ones, hypernovae, which are even more violent. Wolf-Rayet. Wolf-Rayet stars are extremely hot, extremely massive stars that have lost their outer hydrogen layers, exposing the helium-burning cores underneath. Surface temperatures can exceed 50,000 degrees Fahrenheit, and in some extreme cases, they reach over 350,000 degrees Fahrenheit, making them among the hottest stars known. They produce stellar winds so powerful that they blast material outward at speeds of up to 2,000 kilometers per second. These winds carve out glowing nebulae in the space around them, which gives Wolf-Rayet stars some of the most beautiful surroundings of any stellar object. Despite their beauty, they are essentially stars in their death throes. A Wolf-Rayet is what a massive star looks like in the final chapter of its life. Most of them will end as supernovae, and the most massive ones may collapse directly into black holes without a visible explosion at all. Neutron star. Neutron stars are the collapsed cores of massive stars that have already exploded as supernovae. They are incredibly dense, packing roughly 1.4 to 2.1 solar masses into a sphere only about 20 kilometers wide. To put that in perspective, you could fit a neutron star inside a medium-sized city. A teaspoon of neutron star material would weigh approximately 6 billion tons. That is heavier than every human being on Earth combined, all squeezed into a single spoonful. Neutron stars are made almost entirely of neutrons, compressed so tightly that electrons and protons have merged together into a single exotic state of matter. They can rotate at extraordinary speeds, with some spinning hundreds of times per second. The gravitational field on the surface of a neutron star is roughly 2 billion times stronger than gravity on Earth. If you were somehow placed on the surface, you would not just be crushed. You would be smeared into a layer of atoms a fraction of a millimeter thick before your brain could process what had happened. Pulsar. Pulsars are a type of neutron star that emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep through space like the spinning light of a lighthouse. If Earth happens to lie in the path of the beam, our telescopes detect regular pulses of radiation, which is exactly how pulsars got their name. Some pulsars are so precise that their pulses arrive more reliably than ticks from atomic clocks. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and the signal was so impossibly regular that researchers briefly nicknamed it LGM1, which stood for Little Green Men. For a short window of time, scientists genuinely considered the possibility that they had picked up an artificial signal from an alien civilization. The truth turned out to be only slightly less astonishing. A dead star spinning so fast and so precisely that it had fooled an entire team of astronomers. Magnetar. Magnetars are neutron stars with magnetic fields so powerful they break the imagination. Their fields are roughly 1,000 times stronger than those of a typical neutron star, and up to a quadrillion times stronger than the magnetic field of Earth. If a magnetar were placed halfway between Earth and the Moon, it would wipe every credit card on the planet, scramble every hard drive, and pull metal objects out of your hands from across the room. In 2004, a magnetar called SGR 1806-2 released a flare that, in 1/10 of a second, emitted more energy than our Sun produces in 100,000 years. The burst was powerful enough to temporarily disturb Earth's ionosphere from 50,000 light-years away. To be clear, that means a single dying star, sitting halfway across the galaxy, briefly affected the air above our planet in a fraction of a second. Black hole. Black holes are not technically stars, but they are formed from the remnants of the most massive ones. When a star with more than about 20 solar masses collapses at the end of its life, its gravitational pull becomes so strong that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. Stellar black holes typically range from about 5 to several tens of solar masses. However, supermassive black holes, the kind that sit at the centers of galaxies, can contain millions or even billions of solar masses. The first ever image of a black hole was captured in 2019, showing the supermassive black hole at the center of the galaxy M87. If you fell into one, the experience would be deeply strange. Long before you reach the event horizon, gravity would pull on your feet more strongly than your head, stretching you into a long, thin thread of matter. Astronomers actually have a term for this. They call it spaghettification. Quark star. Quark stars are hypothetical objects that may exist in the narrow zone between neutron stars and black holes. In theory, if the pressure inside a neutron star becomes extreme enough, the neutrons themselves break apart into their fundamental building blocks, called quarks, forming a brand new state of matter known as quark matter. A quark star would be smaller and denser than a neutron star, but somehow it would resist the final collapse into a black hole. In 2002, the Chandra X-ray Observatory identified two objects that appeared too small to be neutron stars and too large to be black holes, making them the leading quark star candidates we have. However, their existence has never been confirmed. They remain one of the great unsolved mysteries of modern astrophysics, ghost objects that might be sitting out there in space right now, waiting for the right telescope to finally prove they are real.